Myself Penil Desai. Today my topic for paper presentation is virtual goal guided RRT for visual servoing of mobile robot with field of view constraints. In this article, a virtual goal guided rapidly exploring random tree based visual servoing approach is proposed for non-holonomic mobile robot to simultaneously satisfy the field of view constraint and the velocity constraint during the motion towards the desired pose. For the trajectory planning part, a new virtual goal-guided RRT algorithm is designed to guarantee the FOV constraint and the velocity constraint by iteratively exploring the scaled Euclidean space in the presence of unknown image depth. The RRT and its variants are very classic sampling-based planning algorithms which have been widely used in the navigation of mobile robots. The exploration of the algorithm relies on the extension module for a selected node in the tree to a random one sampled from the state space. For non-holonomic mobile robots, the extension of the tree is performed by the iterative integration of kinetic equation of robot over a period of time. Once the tree extends into the neighborhood of the goal node, the exploration can be considered successful. For large-scale navigation tasks, the end error of the final trajectory is very tiny compared with the whole trajectory, which has little effect on the actual task. However, for visual servoing, the mobile robot generally works in a relatively smaller workspace, and the robot is required to actively arrive at the desired pose. In this case, the end error of the final trajectory has a considerable impact on the system performance. The main contribution of this article are summarized as follows. Number one, an integrated trajectory planning and tracking control approach is proposed to tackle the FOV constraint and the velocity constraint, which consist of trajectory planning in scaled Euclidean space and trajectory tracking. Since the trajectory planning stage is incorporated into the visual servoing, the FOV constraint and velocity constraint can be handled in the planning process and then generally satisfied during the visual servoing process. A VGG RRT algorithm is designed for trajectory planning of the mobile robot visual servoing in presence of unknown image depth. And third, experimental results are provided to validate the effectiveness of the proposed approach. Now let's discuss the problem statement. The figure shows a two-wheeled mobile robot equipped with a fixed monocular camera in the global coordinate system. Let us assume the camera frame FC is coincident with the robot frame. The x-axis is along the optical axis of the camera, which is coincident with the heading direction of the robot, and the y-axis point to the left side of the robot. P represents the coplanar feature points. Let the vector x, y, and theta denote the pose of the mobile robot with respect to the global coordinates. When the robot moves on the xy plane, the kinematics of which can be described as given by equation 1, where v and w are the linear and angular velocity of the mobile robot respectively. For visual servoing of the mobile robot, the real-time pose of the robot is obtained by computer vision techniques, specifically by implementing the homography matrix decomposition method on the current and desired images. The pose of the current robot frame with respect to desired one can be estimated. However, due to unknown depth of the 2D images, only the scale coordinate can be obtained, which is represented by equation 2, where d star is a positive real number and is an unknown constant, denoting the distance from the origin to the desired frame to the plane where the feature points are located. If the desired pose FD of the robot is regarded as the global frame, a scaled Euclidean space up to the 3D space by a factor d star can be constructed, which is shown in this figure. Then substituting the scale translational coordinates from equation 2 and 1, the kinematics of the mobile robot in the scale space can be described as shown in equation 3, where v star is v divided by d star, representing the scale linear velocity of the mobile robot. To improve the dynamic performance, the acceleration signals of the robot can be chosen as the control input. Thus, the discrete pseudo-dynamic model of mobile robot in the scale space is obtained as shown in this equation 4, where a1 star is a1 divided by d star. A1 and A2 are the linear and angular velocity accelerations of the robot respectively. Delta t is the integration step and k is the discrete time instant. Now let us discuss the proposed approach. The proposed strategy consists of two parts as seen in the block diagram. The first part aims to find the image trajectory satisfying the FOV constraint from initial pose to the desired one of the mobile robot. A virtual goal-guided RRT algorithm is presented to search the trajectory in the scaled Euclidean space. Simultaneously, each explored sub-trajectory is projected into the image space to check for the FOV constraint. If the whole trajectory is explored, it is passed to the second part as the reference input. The second part is a closed-loop visual servoing system which ensures the mobile robot can effectively track the given reference image trajectory. Through the whole framework, the mobile robot moves from initial pose to the desired one without violating the FOV constraint. The VGG RRT algorithm for trajectory planning is shown in algorithm 1, which corresponds to the upper block of the block diagram shown in previous slide. The proposed algorithm mainly consists of two stages. First is general searching, that is from line 1 to line 10, and the greedy extension, that is from line 11 to line 21. Now let us discuss in detail the trajectory planning in scale space. Since the desired framed FD of the mobile robot is seen as the global coordinate system, the coordinate of the desired pose is XD. The coordinate of the initial pose FC is denoted as XI with respect to FD. The init tree function initializes the exploring tree T with the initial pose Xi. Each node N of T in the tree represents one state of the mobile robot in the scaled Euclidean space, which is defined as seen in the first equation. Generate virtual goal function generates a virtual goal node right behind the desired pose. Specifically, the virtual goal is chosen as NVG. The longitudinal coordinate of NVG along the x star d axis is same as that of the initial node, and the lateral coordinate along the y star d axis and the heading angle are same as those of the desired node. During the exploring process of the tree, the virtual goal attracts the tree to extend sideways so that the tree is guided into the region right behind the desired pose, which means that the generated candidate edge are easier to satisfy the FOV constraint of the camera. Besides, with the tree approaching the virtual goal node, the lateral error of the mobile robot can be greatly reduced. The virtual goal is one of the key differences between the proposed searching method and the classic RRT. Find near side node function finds the nearest node in the tree to random node rrand. The distance matrix between states is defined as in the second equation, where kx, ky, k theta, kv, kw are positive weight coefficients less than 1. x1 star and x2 star are longitudinal coordinates of two states. X star max is the largest x star value of all nodes in the tree. To guide the tree to extend sideways, the lateral coefficient kv is chosen larger than others. That is, the smaller lateral error of the node, the larger probability to extend. Extend FOV function. Extend the tree from the nearest node n side to the random node n rand under the FOV constraint. The control input u is chosen at random from the permissible control sets. Following each successful extension of the tree, greedy extension is tried from the newly explored node n new to the desired goal node nd with the greedy probability p greedy. If the random node is less than the greedy probability, greedy extension is performed by polar stabilization controller, that is given on line 13 and 14 of algorithm 1, given by the third equation, where V star G and WG are the control inputs of the mobile robot in the scale space along the greedy edges. Now let us focus on checking the FOV constraint in the image space. Once the initial and desired images pi I and pi d are acquired, applying the homography matrix decomposition technique, the direction vector n can be obtained, which denotes the direction of the plane where feature points are located with respect to the desired robot frame FD. Denoting the newly explored state node as ntemp, the transformation from the desired frame to the newly explored one is represented as in the first equation. Combining this equation, the Euclidean homographic matrix H between the desired pose and the newly explored one can be calculated as the third equation. Following third equation, the projective homographic matrix G is obtained by equation 4th, with K being the intrinsic parameter matrix of the camera. The matrix G describes the mapping relation between the desired image and the current one captured at the newly explored pose of the robot. Then the principal coordinates Pi in the current image captured at the newly explored state ntemp can be calculated as given by the fifth equation, where lambda I is a positive real number is a normalization factor. For the calculated homogeneous pixel coordinates Pi at the initial explode pose, if the rules in sixth equation are satisfied, it concludes that the feature points Pi is within the camera FOV at the newly explode pose. If all the states of the edge satisfy FOV constraint, it concludes that the candidate edge satisfies the FOV constraint. Now let's talk about the probabilistic completeness analysis. The lemma 1 stated in the paper states that if there exists a trajectory satisfying the FOV constraint from the initial node N0 to the desired node ND, it is equivalent to existing a trajectory satisfying the FOV constraint from N0 to the virtual goal node NVG and vice versa. So it is interpreted as if there exists a trajectory satisfying the FOV constraint from N0 to NVG, the probability of finding a trajectory is 1 as the number of iterations increases to infinity. According to lemma 1, the probabilistic completeness of the lines 4 to 10 of the code can also be said that if there exists a trajectory from N0 to ND, the probability of finding a trajectory satisfying the FOV constraint from N0 to NVG is unity when the number of iterations approaches infinity. Here we can see in figure A shows a trajectory satisfying the FOV constraint can be found from the initial node to N0, the virtual goal node NVG, if there exists satisfying the FOV constraint from the initial node N0 to the desired node NVG. And figure B shows a trajectory satisfying the FOV constraint can be found from the initial node N0 to the desired node ND. If there exists a trajectory satisfying the FOV constraint from the initial node N0 to virtual goal node NVG. Now let's talk about the trajectory tracking. If mobile robot precisely tracks the given trajectory, it can move from the initial pose to the desired one simultaneously without violating the camera FOV and velocity constraint. Thus, visual servoing task can be completed. Here is the experimental setup used in the paper. The experimental platform includes a Pioneer 3DX mobile robot, a laptop computer, and a DMK23G618 camera. 4 artificial corner points on a coplanar surface placed in front of the robot. The communication with the mobile robot through a RS232 serial port with a camera through a RJ45 port. The image size is of 640 x 480 pixels captured at 60 Hz. The control period in the experiment is 15 milliseconds. The distance from the origin of the desired pose to the plane where the feature points are located is 1.8 meters. That is, D star here is 1.8 meters. When implementing the experiment, the desired image is first captured and stored at the desired robot pose. Then authors first put the robot at the arbitrary initial pose and capture the initial image. Afterwards, applying the homography decomposition technique on these two images, a scaled space is constructed and the scaled initial pose with respect to the desired one can be obtained. Finally, the trajectory planning process is performed and the mobile robot tracks the planned trajectory with visual servoing controller. Let us talk about evaluating the effectiveness of the proposed approach. Here in case 1, when the initial lateral error of the mobile robot is small, 3 experiments were conducted with 3 different initial poses, and the trajectory planning and tracking results are shown in figure 1 on the left. The planning time on the mobile panning time for the above trajectories are no more than 0.3 seconds. In the figure, the red triangle at the origin denotes the desired pose and the red dashed lines are planned reference trajectories, while the blue lines are actual visual tracking results of the mobile robot. It can be seen that the initial lateral errors are less than 0.2 in scaled Euclidean space, which is equivalent to 0.36 meter in non-scaled space. In this case, the initial feature images are almost located in the center region of the image plane, and thus the FOV constraint is easy to be satisfied for the mobile robot. Hence, the planned trajectory smoothly connects the initial pose and the desired one, which are very similar to the results given by existing visual stabilization controllers. In case 2, when the initial lateral error of the mobile robot becomes slightly larger, the initial image of the feature points is close to the image boundary. Simple and smooth trajectories are those in case 1 are impossible to satisfy the FOV constraint. As shown in the figure on the right, the initial pose of the mobile robot is -0.6 and -0.25 in the scaled space. it can be seen that the robot first moves backward from the initial pose to make it approximately right behind the desired pose, and then it smoothly moves towards the desired pose. The planning time in case 2 is 0.7 seconds. Now let us discuss the necessity of the proposed approach for accurate position control. In the first figure, the trajectory planning and tracking results using the proposed approach are displayed. It is seen that the mobile robot turns back twice due to the FOV limit when moving to the desired poses. The trajectory planning time is 1.2 seconds. It should be noted that the planning time varies with different initial pose of the robot. Generally, larger initial lateral error leads to longer planning time, since the tree node needs to consume more exploring attempts to find out the trajectory satisfying the FOV constraint. Second figure on the left displays the corresponding image trajectories of the feature points. It is seen that the image trajectories are always within the given FOV constraint during the visual servoing process. For the same initial pose of the robot, figures on the right demonstrate the experimental results using a visual stabilization control based on backstepping method. In the first figure, it is seen that the trajectory of the robot is simpler and smoother compared with the figure on the left. However, the second figure on the right, it can be clearly seen that the image trajectories of the feature points are out of virtual image boundaries. That is, the feature points are out of present FOV limit of the camera when the robot moving to the desired pose. For the actual visual servoing task, once the feature points go out of the real FOV of the camera, the visual feedback will be unavailable and the visual servoing process will be failed. Now let's talk about the velocity. In the first figure on the left, the blue solid lines denote the planned velocity. The orange solid lines denote the computed velocity commands for visual servoing controller, and the red ones denote the actual velocity measured from the robot, while the green dashed lines are given velocity bounds. Since the velocity saturation constraints can be considered in the trajectory planning stage, it can be seen that the actual velocities of the robot are always within the given maximum range. A sudden change in velocity at about 11 seconds is due to the switch from random sampling extension to the greedy extension. As shown in second figure on the left, the pose errors of the robot all converge to 0, which means that the robot successfully tracks the planned trajectory. And now, first figure on the right demonstrates the velocity profiles of the robot driven by the visual stabilization controller, wherein the blue lines are the velocity commands calculated from the stabilization controller and the red lines are the actual velocity of the robot. Since the velocity saturation constraint is not considered into the controller design process, the actual velocity exceeds the given velocity limits. As far as we know, there have been few visual servoing controllers considering the velocity saturation constraints of mobile robot. Second figure on the right corresponds to the post stabilization of error of the robot. That is all on VGG RRT. Thank you very much and let me know if you have any questions.